Okay, welcome back. This is our second short video lesson on sedimentary rocks. Whether I break it down into 2 or 3, I haven't decided yet. We'll just kind of see how the timing goes here. Alright, so how much battery power do I have? I have decent battery power. Okay, so now what we're looking at are the steps in the formation of sedimentary rocks. So what do we see here? Well, we see a sandstone outcrop on the side of the road, very similar to what we saw in the previous video lesson. Okay, so your first step, I'm always hoping you watch these videos in order, by the way. Okay, so the first step there, it all begins with weathering, the different types of physical and chemical weathering that we will discuss in class, in the narrated PowerPoints, and to some extent here in the video lessons. Okay, so number 1 is simply pointing to those lines, those joints or fractures that form. Step number 2 is erosion. And I will admit that I like to use those two words together quite often, weathering and erosion, because, well, they work together kind of like Batman and Robin, or peanut butter and jelly, but weathering and erosion do not mean the same thing. So weathering is referring to, either physically breaking the rock or altering it, changing it in a chemical way. Erosion is going to refer to individual particles that have weathered out of that outcrop, those particles actually being extracted from the bedrock, as in they're going to fall out of that bedrock. Okay, that could be with wind or just simply gravity, they're washed out with water, or they're chucked out with ice. So erosion is number 2 on this drawing, and I'm pointing to a couple of things. First of all, those dots at the base of the sandstone outcrop are sand grains. Makes sense, it's a sandstone outcrop. You should expect to find a bunch of sand grains littering the base of the outcrop. It's also pointing to that square, smaller piece of sandstone over on the left that clearly has been chucked out of the top left corner of the outcrop there, and frost wedging has a lot to do with that. So step number 2, erosion, the extraction of the mineral grains, these sedimentary pieces from the bedrock. Number 3 is transportation. We see there we're going to pretend that the distance there on that stream is covering, 200-300 miles. All right, so we're going to go from the sandstone in the mountains down to the coast. Okay, so transportation is just simply moving the sediment around, removing it from that area in which it was produced. 3 things here doing the work: water, ice, as in glaciers, or wind. Okay, which of those 3 do you think is moving the majority of sediments on this planet? Well, of course, that would be water. And what size sediments would wind be able to move around? And of course, that answer is going to be tiny grains. Okay, step number 4 is called deposition. All right, so a very long time later, some of those sand grains make their way all the way down to, say, Ocean City, Maryland, because this is that same sandstone outcrop that's on I-68. It's in Maryland. I-68 runs east to west. And some of these sand grains make their way to Ocean City, Maryland, and they simply get deposited. Meaning what? Well, they stop moving around, and they're going to fall out of suspension. So sand gets deposited there at the beach. Okay, in the lower left corner is step number 5, and it's kind of separate from the drawing because I can't really draw that. Step number 5 may or may not even occur. It's called lithification, and you will discover in the narrated PowerPoints that this is when your loose sediment grains actually become rock, solid rock. How long is this going to take? Oh, hundreds of thousands to millions of years later. It's going to take some time, for sure, because it takes time for these things to become buried. So there are 2 bullets there, 2 steps to lithification, and these are expanded upon in the narrated PowerPoint, by the way. Compaction and cementation. Compaction just simply says that the sediments are going to get buried with time as new sediments are deposited on top, and the sediment grains will move closer and closer together. They become compacted. And then cementation just refers to a natural cement showing up that helps to glue the grains together. You're going to learn the natural cements on one of the PowerPoint slides. They're going to include things like calcite, quartz, mud or iron oxides. All right, we are going to go ahead and add some more things. So maybe we'll just have 2 video lessons. And it might take some time for this to upload to YouTube. That's okay. All right, so we're beginning here with something called sedimentary structures. So everything on this, from here all the way going to the right, is going to be sedimentary structures. So these are the drawings I put on the board when we discussed this in class. You will see a further discussion of these things in the narrated PowerPoints. But we're going to start with sedimentary beds. First of all, what do we have? What are we looking at here? We're looking at a layer of sedimentary material. Shale on top, limestone below, sandstone below that, and then several layers of shale below that. Okay, so a sedimentary bed is one single layer of sedimentary rock with a distinct top and a distinct bottom. I have some arrows there pointing to shale and limestone, but every layer there of rock is a sedimentary bed. So what are bedding planes? Bedding planes are these surfaces where you go from one sedimentary bed to another. So there are several bedding planes there, and I have arrows pointing to just 3 of them. Now, if you have more than one sedimentary bed together, you refer to that as strata, and we see that over on the left there. So, sedimentary beds, layers of rock, bedding planes are the surfaces in between them. Moving down just a little bit, sedimentary formation is discussed in the narrated PowerPoint. It is simply a body of sedimentary material, be it rock or sediments, that is distinctive, meaning it doesn't look exactly like any other sedimentary rock anywhere else, recognizable and traceable. Recognizable and distinctive basically meaning scientists have studied it and have written about it in scientific journals and can be traced over a regional distance. So perhaps to some decent distance, but not all the way around the world. So the drawing here is the one that I like to put on the board every semester and discuss it. And I don't know if we'll have time to put this on the board in class or not. All right, so we are looking at a cross-section going from Raleigh all the way down to Wilmington. WILM is Wilmington. And then in between, we also have RP, which stands for Rocky Point, and CH, which stands for Castle Hayne. Those are 2 towns just west of Wilmington on I-40, and they're important to this discussion. So all I really want you to know about sedimentary formations for your second exam is to give me an example of one. So the Castle Hayne limestone, remember LS just means limestone. What's our age on the Castle Hayne limestone? 35 to 50 million years. Remember MA stands for millions of years. And this is a real example. It's not made up, and it's a relatively local example. This is occurring in the southeastern portion of North Carolina in the coastal plain, and it does dip kind of southeast at about 20 degrees. All right, so first thing I'm going to point out is that limestones are marine rocks, meaning they form in a saltwater environment. So I want to point to the drawing there where you see in blue, because we always use blue to denote limestones, CHLS, that's the Castle Hayne limestone. That's a drawing of what it looks like in a cross section, dipping down to the southeast at 20 degrees and outcropping or sticking up out of the ground at the towns of Rocky Point, RP, and Castle Hayne, CH. It is named for the town of Castle Hayne. And then you have Raleigh over there to the west. You know, what's your distance in between Raleigh and Rocky Point? I don't know. More than 60 miles, I'm guessing. Okay, so if limestones are formed from seawater, I'm going to ask you guys a question. You see where seawater is presently in the drawing there. Okay, it's down there at the edge of Wilmington, at Wrightsville, the eastern edge, I should say, at Wrightsville Beach or Carolina Beach. So what must have been true about sea level during that time span of 35 to 50 million years ago? Let's let you think about that for a few seconds. Looking at where we find the Castle Hayne limestone today and taking into account that limestones are marine rocks, sea level was higher back then during the Eocene. Okay, how do we know that? Because it deposited a bunch of limestone further inland than sea level is today. What about Raleigh? Okay, back then in the Eocene, 35 to 50 million years ago, was sea level as high as where Raleigh is today? The answer is no. Why do we say that? Because the Castleton limestone doesn't go all the way to Raleigh. Okay, we are going to scoot a little bit again, and we are going to move on with more sedimentary structures. Okay, so we're still under this larger title here of sedimentary structures. Ripple marks. These are small ridges that form perpendicular to water flow. So when they get preserved in the rock record, they tell you something about what were the conditions like geographically here when this rock formed. And the answer is, well, there was water here, or we wouldn't have these small ripple marks. What kind of water was it? Well, the shape tells us. Number one there, those are symmetric ripples. As in, if you draw a line down the middle, it looks the same on one side as the other. These are also referred to as wave-formed ripples. So in what kind of water environment are symmetric ripples going to form? And the answer is oscillating, as in the water flow back and forth in two directions, as in tides. Okay, so ripple marks can form in marine environments. They can form in the back barrier marsh tidal flats between a barrier island and the mainland. Number two, those are asymmetric ripples, meaning if you draw a line down the center, they do not look the same on either side. So the asymmetric ripples are also known as current ripples, and they show us that the water flow was in one direction only, and that of course means rivers or streams. All right, we're gonna move again. Keep having to move these chairs around, and then whoever teaches in here tomorrow will have to scoot them a little bit more. All right, so we are now going to look at dunes. So we are still in this title of sedimentary structures, dunes. So think about dunes that you've seen on the beaches, maybe in the Outer Banks. They still have some healthy dunes. Some beach areas, they've bulldozed the dunes to put up more hotels. That's a shame. Dunes are important. They help protect structures that are behind them. Okay, so dunes are ridges like ripple marks, but they're much bigger. They're large ridges. So in the case of ripple marks, the ridges are small, like centimeters in height, millimeters to centimeters in height. In dunes, they're larger. They're tens of centimeters to meters in height. So these are large ridges in sand, and they form not from water, but from wind, as wind moves the sand around. Now, there are pictures of dunes in the narrated PowerPoint, by the way. Dunes may show something called cross-bedding. So I have a drawing there of cross-bedding. So in our drawings so far this semester, where we're showing rock layers, they've all been, well, pretty much horizontal, flat line, parallel to each other. What you see in the cross-bedding is that things are no longer parallel. You might have a couple small layers that are flat lying and parallel, but then what is below it is at an angle. And then below that, you might get some flat lying beds again, and then below that, you get more that are truncated at an angle. Those are cross beds. There is a picture of at least one cross-bedded sandstone in the narrated PowerPoint. Now, if we should see large cross-bedded sandstones in the rock record, like we find at Zion National Park, what does this represent? And the answer is it represents ancient desert dunes. Okay, so Zion National Park is in the American Southwest, what we sometimes refer to as the desert Southwest. So the area is relatively dry, but in the past it was an actual desert with big sand dunes being moved around by wind. How do we know that? Because there are huge, giant cross-bedded sandstones there. Okay, below that we have something called graded beds. And the graded beds are these layers that are stratified or layered according to grain size. So the drawing there, you see we have large, like cobbles on the bottom, big round open circles, and then above that they're a little smaller, maybe they're pebbles, And then above that, they're a little smaller still. Maybe they're large sand grains, and then smaller sand grains, the dots on top. When you see graded beds in the rock record, what they represent are submarine landslides, also known as turbidite flows, which may happen on the continental shelves. And then if you find mud cracks in the rock record, they represent, well, periods of drying out. So it could be an arid region, or sometimes you might have mud cracks that form on the tidal flats during low tide. Those might also possibly be preserved in the rock record. And of course, fossils. Fossils are definitely considered to be sedimentary structures. So in general, sedimentary structures tell you something about the environment in the past. Okay, we're gonna go ahead and just we're gonna have 2 videos, not 3, and we're gonna move, and we are going to look at our last topic for this video. Okay, so, all right, what we're looking at here is what a marine transgression would look like in the rock record versus a marine regression. So I discussed these things in the narrated PowerPoints. A transgression is a sea level rise, like what is happening today. Okay, and this can be eustatic sea level rise, as in global, or it could be a local sea level rise, as in something that's occurring in just one location. Now, in the narrated PowerPoint, I do discuss the difference between eustatic global sea level rise, which can be brought about due to natural climate variations and or anthropogenic climate change, versus local sea level rise. And I think the examples we discuss in there are the fact that New Orleans, since it is sinking, will experience a greater local sea level rise than eustatic. And the flip side of that would be the example of the Pacific Northwest, where because there is a subduction zone plate boundary offshore, the land is actually rising. So while the Pacific Northwest will experience sea level rise, eustatic, global, what's happening now, their local sea level rise will be a little less pronounced because the land is rising. Although to be fair, sea level is outpacing tectonic uplift pretty quickly. All right, so how do we recognize in the rock record where we have had a sea level rise or sea level fall in the past? Sea level rise, again, is referred to as a marine transgression. So we're looking at 2 stratigraphy columns here, meaning columns of rock. Okay, these could be exposed at the surface, or maybe we took core samples where we drill down into the subsurface and bring up these core samples to get a look at what's beneath our feet. So over on the left is the marine transgression. So you have rock in this particular order. You have limestone on top. Limestone is a marine rock, as we mentioned earlier with the Castleton limestone. Below that we have sandstone, say a beach sandstone. Below that we have shale that perhaps was from a meandering river in a coastal plain, like say the Lumber River or the Cape Fear River. And below that we have something called breccia, which is a land-based rock. Breccia is a poorly sorted rock where the large grains are angular, and it basically forms in the mountains or close to the mountains, coming down the mountainside. So what's important here in this stratigraphy column on the left is that the marine rock is on top, the limestone is on top. So that's a transgression. All right, let's move over to our last topic for our last video lesson for sedimentary rocks. How about a marine regression or sea level fall? Has that ever happened in the past? Yes. Anytime we're going through a glacial maximum, also known as an ice age, we are going to have a sea level fall. So what does that look like in the rock record? In this case, your marine rocks, saltwater rocks, are on the bottom. Chalk is a type of limestone. It's a deep water limestone. So we have chalk on the bottom, deep water limestone. Then we have maybe a fossiliferous limestone on top, which is more shallow but marine. On top of that, we have a sandstone that looks very much like a beach sandstone. On top of that, we have shale, which again could have formed on the floodplains of meandering rivers in the coastal plain. like the Lumber River, and on top of that is a conglomerate. A conglomerate is a land-based rock. It is poorly sorted and it has large grains that are rounded, and it tends to form in braided streams that are in the mountainous areas. Okay, so this last topic is basically recognizing marine transgression versus marine regression in the rock record. That'll do it for our video lessons on sedimentary rocks.